Welcome all. In last lecture, we study regarding adder circuits, that is n-bit parallel adder, 4-bit parallel adder using 7483 and 74283 ICs. After that, we have seen a subtractor circuit using a adder circuit. Today we will see a 4-bit parallel adder and subtractor. That is, in this we are going to study a common logic which will act as a adder as well as a subtractor. The addition or subtraction of two 4-bit binary numbers can be obtained using the circuit shown over here. The operation performed by this circuit depends on this mode select input M, which will going to decide either this circuit is going to act as a adder or this circuit is going to act as a subtractor. The number B, which is to be subtracted or which is to be added, is applied to this adder through 4 XOR gates. These are the 4 XOR gates. Through this input, that is number B, is applied to the adder circuit. One input of each XOR gate is connected to mode select input M, and other inputs to the XOR gates are B3, B2, B1, B0, that is 4-bit binary number which is to be subtracted. This is the number A. Number A and number B are going to be added, or the subtraction operation is to be performed, and the result of addition or subtraction, that is sum or difference, we will get at this output S0, S1, S2, S3. Cout is the final carry output. Now here we can observe that a carry input is connected to mode select terminal and second input of each XOR gate. That is, carry input and mode select inputs are shorted together. Now we will see the operation as a adder. Now I have taken only this much picture in the next slide so that we can understand how these XOR gates going to act. Now here the circuit is shown. Now mode select input M is made 0 so that this circuit can act as a adder. Now we will see how this M as a 0 will force this circuit to act as a adder. Now when M is 0, the output of XOR gates will be same as the number B, which is applied at their inputs. This is because the 0 XOR 0 will give you 0 and 0 XOR 1 will give you 1. Now we will see here that the mode select input is made 0, that is, this XOR gate will have a 0 input over here. This is the 0 input, this is the 0 input, and this is the 0 input, and another input is B3, B2, B1, B0. Again, also the truth table of XOR gate is also shown over here, in which we have to observe these two combinations, that is, when M is 0 and this B is going to change, it will be either 0 or 1. Now we will see in detail, in brief, during this explanation of example, how the input number B will remain same as it is at the output of these XOR gates. The carry input is connected to M, so C input is also a 0. Therefore this adder acts as a adder which will add A plus B plus C in, that is as a plus B. Now we will take one example to get understood this concept of addition. Here the M is made 0. The input, that is B3, B2, B1, B0 are 0, 1, 1, 0. That is, number B is 6, and we have considered the number A as a 0, 0, 1, 1, that is 3. as mode select input m is 0, this is going to perform the addition, and we will get result as a 9. Now we will see how we can get this result as a 9. Now here b3, b2, b1, b0, b1, and this is a b0. Actually it is over here by mistake b1 is written, b0 are 0 1 1 0. Now if we observe this XOR gate which is having a b3 input, that is 0, and another input is m input, that is mode select input, which is also 0. So output of XOR gate will remain as a 0 for b3 case. Now if we observe b2, b2 is 1 over here, b2 is 1 over here, and another input to the second XOR gate is m, that is 0. Now when m is 0 and b2 is 1, the output is 1. So the b2 will also remain as a 1 at the output of XOR gate. After that, if you observe this third XOR gate which is having a b1 input and m input, b1 is 1, m is 0. So we can observe this combination for 0 1 XOR gate will give a 1 output. So we will get a 1 output at the output of XOR gate. And last one is b0, which is a 0 input, and another input to this fourth XOR gate is 0. So 0 XOR 0, that is this combination will gives you a 0 output. So this is how by keeping m 0 we can get the number b as it is at the output of XOR gates, which are again applied to this b3, b2, b1, b0 pins of the 7483 ICs. Now this is the number b which we get at the output of XOR gate. Another number a is what? 0 0 1 1. This is the BCD adder circuit. So it will going to add these two numbers, 1 1 plus 1 0 1, 1 plus 0 1, 1 plus 1 0, carry 1, 0 plus 0 0, 0 plus 1 1. This is the value of 9 in binary. So this is how we can add the two numbers by setting mode select input to 0, by which a number b will not going to change, it will remain same at the output of each XOR gate as it is. Now next we will see a 4-bit parallel adder subtractor with mode select input 1. Now here mode select input is made 1, so that this circuit is going to act as a subtractor. Now we will see how this is going to happen. Here mode select input m is 1. The output of XOR gates will be inverted number of b, which is applied at their inputs. This is because 1 XOR 0 will gives you 1, the 1 XOR 1 will gives you 0. Here the 1 is mode select input, and another input is the our actual number b input, which is inverted. This is here it is 0, it is converted into 1. Here it is 1, it is converted into 0 by keeping mode select input 1. As each bit of word b is inverted by XOR gate, we get 1's complement of number b. Now before that, keep in mind that this circuit is going to act as a subtractor using 2's complement method, in which we have to find out the 2's complement of the number which is to be subtracted. The same procedure is going to be followed by this circuit. The carry input is connected to m, so that carry input is now become as a 1, as we made mode select input as a 1. The inverted number b adds this carry input 1 to give 2's complement, and we are going to add this complement of b, and actually the addition of complement of b with a is nothing but a subtraction, that is a minus b. This is how the circuit acts as a subtractor using 2's complement method. Now we will see in brief with examples. Now here again by mistake m is shown 0, This is a typographical error, actually it is 1. Now we have taken in a example that number b as a 0 1 1 0, that is our number b is now what, 6, and number a is 0 0 1 1, that is 3. So this circuit will going to perform 3 minus 6, and we will get the number as a 3. Now we will see how we can get this number as a 3. Now if we see B3 is 0 and another input to this first XOR gate is 1, that is M as a 1. So 0 1 or 1 0 will gives you always 1. So B3 will become as a 1. After that, for second XOR gate, B2 is 1, mode select input is also 1. So for 1 1 we will get 0. So I can write over here as a 0. I am writing the output of XOR gate over here. Now next B1 is 1 for this third XOR gate, and another input is also 1. So 1 1 will give you 0 again. Now last B0, this is also a B0, by mistake it is written as a B1. B0 is 0 and another input M is what, 1. So for 1 0 we will get 1. So we will get output of XOR gate as a 1 0 0 1. Now this is the inverted version of this number B, that is we can call it as a 1's complement of B. Now as carry input is connected to M, which is 1, so before starting the addition, this 1 is going to be added into this, which will gives you 2's complement of number B, that is we can get over here as 1 plus 1 0, carry 1 1 0 1. So I can get now the 2's complement of B as a 1 0 1 0. So this is my number B, 1 0 1 0, which is 2's complement of number. This is 2's complement of B, as 1 is added in the 1's complement of B. Now number A is what I have considered over here is 0 0 1 1, 0 0 1 1. Now I am going to perform the actual addition. 1 0 1, 1 plus 1 will give you 0 with carry 1, 0 plus 0 0, 0 plus 1 1, 0 plus 1 1. This is the output of our adder circuit. Now here if you observe, the carry is what, 0. As carry is 0, our result is in what, negative form, that is 2's complement form. So our result is what, 1 1 0 1. Now we have to take 2's complement of this number as carry is 0. So simply I can take 1's complement of this as 0 0 1 0, and I will add a 1 into this to get 1 1 0 0. This is what, a 3. This is how we can get a 3 minus 6 as a 3. This is how a 4-bit adder acts as a subtractor by connecting mode select input to the binary 1 using 2's complement method. Next we will see a BCD adder using 7483 IC. BCD adder adds 2 BCD digits. We already know the rules of BCD additions, and the addition will, during the addition the rules of binary additions are going to be followed. We know these rules already. We learned this in the first chapter. If sum is less than 9 or equal to 9 and carry is 0, then no correction is necessary. The sum obtained is correct, is valid, and is in true BCD form. If sum obtained is greater than 9, or if a carry is generated, that is 1, then correction is necessary, as we get this wrong sum, that is invalid sum, that is invalid BCD. To convert a invalid sum, wrong sum, invalid BCD, into a valid BCD form, we have to add a 6 into the obtained sum, so that we can get a sum into the true form or a valid BCD. These rules we have studied already. Now based on this, we are going to design a BCD adder circuit using IC 7483. Now this is the block diagram of BCD adder using IC 7483. As per the rules of BCD addition, the 4-bit BCD adder should consist of the following blocks, by which all the rules can be followed by the circuit which we are going to design. A block diagram should consist of a 4-bit adder, which is shown over here, to add two 4-bit BCD numbers A and B. For addition of these two BCD number, we need a one adder, which is named as a adder 1. After that, we need a combinational circuit which checks this sum of binary addition, whether the sum is greater than 9 or if any carry is generated from this addition. So to check the sum greater than 9 or to check whether the carry is generated or not, a combinational circuit is required. So we are going to design this combinational circuit, to which there are two inputs. The sum input is connected to this, so that a sum is greater than 9 or less than 9 can be checked by that, and a carry input is also, carry output of adder is connected as an input to this, so that whether carry is generated or not can be checked by this combinational circuit. And output of that combinational circuit is connected as an input to the next 4-bit binary adder, which is going to add a 6 into this obtained sum to correct the wrong sum. Now we will see how this 6 can be added into the wrong sum in next slide. Another 4-bit binary adder we require, that is this one, to add a 6 into the incorrect sum, which I already told. So we have to design a combinational circuit that finds out whether the sum is greater than 9 or a carry is 1. In both these cases, our sum is going to be a invalid, so that we are going to check for that. We have to check for that. Now we are to design a combinational circuit. This is our combinational circuit, which is having 4 inputs, S3, S2, S1, S0. These are the 4 inputs of our combinational circuits, that is some bits of our adder 1, and we are going to keep this output Y 1 or 0. Now in this, as the inputs are 4, there are 16 combinations from 0 0 0 to 1 1 1. Out of these, up to 9 output Y is kept as a 0, as BCD numbers from 0 to 9 are a valid BCD numbers. After that from 10 to 15, the output is kept as a 1, which detects the invalid BCD number. We already know we cannot show the 10 number in BCD as 1010, 11 as 1011, 12 as 1100, 13 as 1101, 14 as 1110, and 15 as 1111. These all are invalid BCD numbers. Therefore, output Y is kept as a 1. Now we are going to enter these Y into this 4-variable K-map, in which these are S3, S2, these are S1, S0 entries. So we are going to make entries all output of Y for each combinations. First 4 are 0, that is 0 0 0 0. Next 4 entries are also 0 0 0 0 0. After that, these are 0 0, that is 0 1 2 3 4 5 6 7, that is 8 and 9 are 0 0, and all rest are 1. This is 1 1 1 1 1 1. Now here octet is not possible, a chord is possible. This is one chord and this is another chord. So for this chord we get the term as a S3 S1, and for this chord we get term as a S3 S2. This is the equation of output equation of combinational circuit by which we can detect whether the sum is greater than 9 or less than 9, or whether the carry is generated or carry is 0. This is based on this equation. A combinational logic circuit is drawn over here. S3 S2 is connected to this AND gate, and S3 S1s are connected to this AND gate, which will produce a Y output. Now this Y will give you a sum is greater than 9 or 0, and this C out will gives you a carry is 1 or 0. We are combining both these using this OR gate, which will give any one condition at the Y dash, whether sum is greater than 9 or less than 9, or whether carry is 0 or 1. We can detect using this additional OR gate. Now this Y dash is connected to the another 4 inputs of binary adder, second binary adder, B3, B2, B1, B0. Out of that, this Y dash is connected to B2 and B1, and B3, B0 are connected to ground, by which a B3, B2, B1, B0 will always be 0, 1, 1, 0, that is 6, which is we have to add into a wrong sum or invalid BCD. For that purpose, B3 and B0 are permanently connected to 0. The sum output of adder 1 is applied to A3, A2, A1, A0, that is these are the sum output of this 4-bit binary adder. The output of combination circuit is to be used as a final output carry, and the carry output of adder 2 is to be ignored. After the BCD addition performed by this adder, if sum is less than 9 or C out is also 0, then we will get Y dash as a 0. If sum is less than 9, then here we get, I will show you with example. Suppose if sum is less than 9, for example, if we consider the sum is right now 7, that is 0, 1, 1, 1, sorry, this is our MSB bit 0, 0, 1, or we will take a 5 number, that is 0, 1, 0, 1. Now S3, S2 are what? S3 is 0, S2 is 1, so we will get a 0 over here. S3, S1 is what? S3 is what? 0, S1 is 0, so we will get 0 over here. So output of this XOR OR gate is 0. Now we have considered in this case carry is also 0. This is 0, 0 or 0 will give you 0. So this B3, B2, B1, B0 will become 0, 0, 0, 0. So we are not going to add anything into this sum, as the result is valid. Next, for these two cases, if sum is greater than 9 or and carry is 0, or sum is less than or carry is 1, we will get a Y dash as a 1, which makes this B3, B2, B1, B0 as a 0, 1, 1, 0, by which a 6 is going to be added into this sum, and we will get a valid BCD at the output of second adder 2. This is how we can design a BCD adder circuit using 7483 IC. Thank you.